Good afternoon. I am so excited to start a series of lectures on the subject that we're going to start today. In fact, this is something my own research lab thinks about all the time. How to develop models in science and engineering. And more recently, how can we incorporate data-driven approaches to develop better models? What I hope is the outcome of this lecture is that you can think about how you can pull different types of modern approaches, machine learning, neural networks, artificial intelligence, and other data-driven approaches in your own science and engineering research. Well, there's a lot of hype and promise and over-flashiness related to the use of different data-driven approaches in science and engineering. I'm going to normalize some of that hype by showing you very specific, concrete examples based on the subjects that we've been covering in this class. Diffusion equation, the heat equation. And you can see how we can develop different models, and actually it'll evolve into kind of a philosophical consideration on what even is a model. How should we develop a model? How should we trust it in the first place? And how can we use that model? So let's pin our discussion by first discussing something that we've been seeing in this class over and over. This is our favorite heat equation, or the diffusion equation if you're solving for concentration. Now, the basic idea behind this model is that it takes in as an input position and time, and it spits out temperature or concentration. So you already know from the solution to this 1D heat equation that at the end of the day, you have a temperature profile that's going to have a summation of a bunch of sines and cosines, an exponential decay term that depends on time. And so for a particular point in space, at that time, you know exactly what the temperature is. So this is an example of a model. You have inputs coming in, space and time. I want to know the temperature inside this room at this point at this time. Well, I have a model for what my temperature is at that point in space and in time. So we've been taking this model kind of for granted and just saying that this is the truth, the absolute truth. This is the law, and therefore we know exactly what the temperature profile is. Well, in reality, the world is very complicated. And in fact, your own research problem is likely dealing with a very complicated system in a very complex material. So it's going to be very unlikely that a simple diffusion equation or the heat equation is the right model for your complex material or complex system. The climate is complicated. Complex materials are extremely complicated. What if I wanted to develop a temperature profile of a composite polymer film undergoing nonlinear plastic deformations, and due to those plastic deformations, it's dissipating heat through a chemical reaction happening inside this polymer, and I want to now predict a temperature profile inside this material? There's no way that a cute, simple little closed set of equation of the heat equation is going to predict accurately like complex polymer film. That's just unlikely that's going to happen. So while in theory and in principle, this type of model where you start from a conservation balance, you write down a constitutive relation where again you have to model that, and out comes a nice equation that you can solve to predict some kind of dynamics or material property. All that, while it sounds nice, is oftentimes impractical. Most complex materials that we encounter in science and engineering is not going to be a nice little equation that you can write down. For example, you might have some sources in sinks. You might have a complex chemical reaction happening inside your slab, the material, and it's exothermic, so it's generating heat inside your material. And you don't know what this function is because it's just a composite polymer radical polymerization. You have no idea what this function is. Or maybe the temperature profile is coupled to some fluid flow, and so this equation is coupled to a momentum balance. Just like that, here's a momentum balance. We don't know what the stress tensor is because you're dealing with a non-Newtonian fluid with an unknown relationship between the strain rate and the stress tensor. So you can't just solve a closed set of equations and predict your material phenomena. Ideally, in an ideal world, we would have this first principles calculation where you write down all the molecular interactions of your atom, you coarse grain that, you get a nice continuum PDE that perfectly agrees and has all the right physics, chemistry, and biology to predict all the properties in your material. That would be an ideal world. Good luck with that. We're probably never going to achieve that kind of situation. So while, again, this sounds nice in theory and principle, it's oftentimes impractical. I'm going to call this the white box model. And I've called it the white box because everything inside this box is absolutely clear. We know each term that we can write down in our governing equation, and if we have all the right physics, chemistry, and biology in these equations, in principle, it should, given my x and time positions, it should predict the right temperature, if it's the right model. Now, the other extreme polar opposite, on the other side of the universe, is a purely data-driven approach to developing a model. That approach completely ignores all physics, chemistry, and biology. It assumes no human knowledge of anything. It throws away 400 years of physics, and it says, if I just collect experimental data points, feed it into a box, can I develop that box in such a way that I'll know my temperature profile? And let me give you a concrete example of this type of modeling. So let's go over to the screen and look at what this type of modeling looks like. So what I've done here is to create a pseudo-experimental data set. Let's suppose that we were to go outside, and you go outside and you measure the temperature using a thermocouple outside your home. And you measure that temperature over some period of time, and you go out there every 10 to 30 minutes, you measure a temperature, and you continue that for 24 hours. So what I'm showing you here is data on the y-axis showing the temperature, so it's your thermocouple reading of the temperature outside your home as a function of time. And let's suppose you started at midday, so the temperature is the highest at time t equals 0, and you do that over a 24-hour cycle. So of course, at midnight, it's going to be very cold, and it's going to ramp back up again at 24 hours later. So let's suppose there's some noise. Of course, there's noise because you're measuring the temperature outside, and you're going to have some fluctuations, but there's going to be some trend hidden behind all that noise that will start high at midday, go down in the middle of the night because it's cooler, and then go back up again during the middle of the day. Now, let's suppose that we were to take a purely data-driven approach. We're not going to know anything about any of the physics and just take the data only over this 24-hour cycle from time t equals 0 all the way up to time t equal 24 hours, feed that into a neural network. So what we're doing here is we're generating a neural network where I'm using the built-in MATLAB neural network generator with 3 layers with 10 nodes each. So I have 10, 10, 10, and I'm going to train that neural network model using data that I'm going to feed in from time t equals 0 to time 24. Okay, so let's draw on the board what we're doing. Okay, so what we're doing is we're putting, in this particular case, just the time input, because we're assuming well-mixed systems, so there's no spatial dependence, into a neural net, which you've probably seen these diagrams all over the place, but there's some number of nodes present, number of layers, and out comes some output, in this case, temperature. Now, what we're doing with the training process is we're inputting data, a bunch of temperatures over the 24-hour cycle. So time going in from 0 to 24 hours goes in, and then out comes temperature. Now, the initial guess of the neural network and all these nodes connecting is going to be very, very wrong, and therefore we're going to say, oh, it was wrong. Please iterate and adjust those connections so that I have a mapping from 0 to 24 hours, all those time points, to a temperature that agrees and fits with the data. So it's training whatever the connection of all these nodes in such a way that my input of time going in accurately represents the output of temperature as shown in the data or as inferred from the data. But everything inside of here is a complete mystery. We have no idea what's going on. All this block sees is a list of numbers coming in, 0 to 24 hours, just numbers coming in and numbers going out, temperature going out. In fact, this block doesn't even know they're solving a heat equation, doesn't even know that your input is time and your output is temperature. It just sees a pattern recognition of numbers coming in and out. So it's more of a pattern recognizing entity, more so than it's helping you solve an actual physics problem. All right, there are plenty of instructional material and videos on what's actually happening inside this block. I'm not going to focus on that. That's not the point of my lecture. In fact, unless you are a computer science engineer developing specifically this type of block or an LLM researcher, for most science and engineering researchers, you're going to be a user of this block and think about how you can use this block in different aspects of your research. So it's not so much important how you understand what's happening on the inner workings of these guys as much as thinking about how you should use this block. We'll get to that in a little bit. But first, I just want to show you the result of this process in the MATLAB code. So once again, I fed in the x-axis, which is our inputs, time points from 0 to 24 hours, and as an output, I gave it temperatures that I've trained. So it's trained all the nodes and all the parameters all connecting each other. And out came this plot right here. So what I'm showing here again is same data, temperature as a function of time. The black symbols are the raw data. And the gray background that I'm shading here is the training data. I've trained this neural network model over the data between 0 and 24. And what you can see is that within this range, the red curve, which is the output of the neural network model, does a pretty good job inside the training set. So at 0, it is capturing the mean, it's going down, it's hitting all the average positions, and it's going back up. So if you just saw this region that we've trained from 0 to 24 hours, you would interpret that the neural network model is pretty good. And it is good at interpolation. But as you will see, if we just deviate a little bit away from the training set, for example, this is tomorrow's temperature. So beyond 24 hours, you kept getting temperature readings. And if you wanted to predict the temperature tomorrow, this neural network would do a terrible job. Look, it's jumping way down after 24 hours. It's going way down to a nonsensical value that doesn't even go through the data at all for tomorrow's temperature. Once again, this neural network is just taking numbers in, numbers out. It knows zero physics. It doesn't even know that tomorrow's temperature is roughly going to be the same as today's temperature. It doesn't know any physics at all. Okay, so this is the basic idea behind how a neural network model could be developed using data. So this is the extreme polar opposite from what we explained earlier with the white box model, because we have no idea what's happening inside this box. So we're going to call this the black box model. Now, think about what we would need to do to predict the temperature tomorrow using a purely white box approach. Let's see, we would need the conservation of energy because ultimately we want to predict the temperature outside your home, but then you also have input parameters of where you live, what altitude you live in, where on Earth you live in, what's your humidity, what's your elevation that you live in, how much ozone and PM 2.5 do you have? Do you have a factory nearby? Oh, then that means that you have to predict the concentration profile of the ozone radicals and the PM 2.5s that then couple to all of your reactions happening inside the atmosphere that then also couples to wind and fluid flow of the air across your city. As you can tell, it becomes an extremely complicated model, and you have to have a 17-step organic synthesis chemistry reaction rate that's somewhere in here as well. It becomes incredibly challenging if you were to purely think about writing down a first principles equations to predict the temperature outside your home. So, what I'm going to talk about now is the middle ground between these two extreme routes of going about developing a model. They're both models. It's just they're both not good for different reasons. This one, it's too complicated. You're not going to be able to actually develop a practical model that you can use. This one, you learned no physics at all. And besides, outside the training data set, it's doing miserably. So if there's some way to combine some physical insight or some intuition that you have over the physics of your system with some aspect of computation together, that could be extremely powerful. So let's consider the following. Although the equations over here might be extremely complicated and the physics might be really hard to understand, we have some physical intuition that tomorrow's temperature is roughly going to be the same as today's temperature, as the same as yesterday's temperature. Of course, 6 months from now, the outside temperature could be very different from today because you're in a different season. But we have this basic fundamental physical insight that there's some periodic driving that happens over a 24-hour cycle. I've just represented that periodic forcing as this function, cosine of the argument pi times time t divided by 12. And this is supposed to represent some kind of periodic forcing that happens over a 24-hour cycle. Of course, the frequency is 2 pi over the period time t, and therefore for 24 hours, there's the factor of 2 upstairs that cancels, and you get a 12 on the denominator. So this is some 24-hour periodic forcing that happens, and that kind of makes sense. Midday, it's the warmest because the sun is hitting, and at night, the sun goes away, all the chemical reactions die, and so it dies away, and it ramps back up again. So there's some kind of forcing that causes your thermal energy to change outside your house every periodic 24-hour cycle. So then you would expect then that the output, the temperature, might also follow a similar periodic cycle. So it wouldn't be inconceivable for us to make a guess that the temperature is going to be under some 24-hour periodic driving as well. So from a physics-informed standpoint, we might expect that the temperature profile can be written as a Fourier series of a bunch of sines or cosines added together. And the reason why we're taking multiple modes is because if you have a forcing that is a single mode, all the nonlinear couplings inside the equation might advance or downgrade the mode by 1 or 2 or more, and therefore you might get some mode coupling that advances to a higher or lower frequency. That's a detail. But it might be reasonable to expect the temperature outside to follow some kind of sinusoidal frequency and model. So of course, the idea is how are you going to get the weights? If we pick out the right weights for each of these frequencies of sines and cosines, then we might be having a good model. So what we're going to do here is to enforce the basic structure of having a cosine function in here, but try to figure out what the weights are and use data to figure out the weights a sub n. So what we've done is to constrain all the possibilities of the relationship between time and temperature into one in which I isolate and say, oh, I know that my temperature is going to be sinusoidally oscillating over a 24-hour cycle, and all I need to know is the weights for each of those frequencies. Therefore, we're still going to take some aspects of this data-driven approach to figure out what this a sub n is. So my architecture that connects my input, which in this case is time, to my output, which is temperature, might look something more like this. So we're feeding in the physical intuition and insight that the temperature, the output, must have some sinusoidal form, but we don't know what the coefficients a sub n are. We're going to use some kind of data-driven approach. It could be a neural network. As I will show you for this specific example, it doesn't need to be a neural network. We could just use linear regression. But in general, in examples that we'll cover later in this lecture, it could be some kind of neural network or machine learning model that connects the inputs t, time, to the coefficients a sub n. So the key difference between what we have here and this purely black box model is in the black box, this neural network is learning the dependence from time all the way to temperature. Here, this black box element, this neural network block, is understanding the relationship between input t and a part of your solution, only the weights of your Fourier series. And I'm going to combine the two together, and out comes my output, which is what I want, the temperature. That's what we want at the very end. And therefore, I can use data that we already have collected in our experiment of the temperature and the time, feeding in this information about the Fourier series, so combining physics and the neural network together to make our model from both a physics-induced approach where you fix it and constrain it to be a Fourier series, and also this aspect of a black box where you rely upon a computer to find a relationship between some input and output. Because in this particular case, the input is time, the output of this neural network would be the weights, the coefficients. And this coefficient actually contains the really hard aspects of this problem. Like I said earlier, it might be coupled to a bunch of equations with lots of organic chemistry involved and lots of biology, physics, and chemistry that's all in here. But at the end of the day, that may all whittle down to some kind of complex dependence inside your weights to your Fourier series. So what we're doing is we're using our human insight that, oh yeah, tomorrow's temperature is roughly going to be the same as today. There must be some periodic forcing involved. And therefore, my temperature would also expect to be undergoing some kind of 24-hour cycle throughout the day. That physical insight significantly constrains what the neural network has to do, because all it has to do is to now find a part of the solution. And it's actually finding what is actually hard for a human to do, which is to abstract all of these chemistry and physics and biology into a very complicated dependence into the weights a sub n. All right, so let's see what this looks like according to this type of approach in our toy example problem. So now, what I'm showing you here is the same data I showed you earlier of the temperature as some function of the time from 0 to 24 hours. The red was the black box, and the green curve is this approach that we've shown here that combines physical insight with a data-driven approach. What you can see is that the green curve agrees with the data very well, not just within the data set that I fed to learn the data-driven part of the block. Again, I only use data between 0 and 24. That's the only data that this model here knows about. So this neural network block, or the data-driven block, only knows about data between 0 and 24 hours. But you can see that it is very, very good at extrapolation as well. I can go very far away to tomorrow, the day after tomorrow, and you can see that all the data are still roughly fitting, even though the black box model is very wrong. Okay? So this approach of combining some kind of physical insight to constrain the search space to a smaller space and let the computer do the part that's really difficult for human is the philosophy behind this approach. And we're going to call this the gray box model. And this is called a gray box model because inside this box, there are some aspects that are driven by physics. It's a physics-informed part of the box. But then there's also this element that takes ideas from data-driven approaches where we're not really sure exactly what happens to the complex relationship between all the data coming in and a part of our solution. Now, I drew neural network block right here, but for this specific problem, very, very simple toy problem, it doesn't even require a neural network. Because let's think about it. We have outputs as temperature. We're expanding in this basis function. We can rewrite our problem in the following way. First of all, we're saying that the temperature can be written as a Fourier series, and I've just expanded out the first couple of terms. And notice that we have experimental measurements on the temperature, and we know the time, that's our input, and so we know all of these terms, and we just have unknowns A0, A1, A2, all the way to the upper bound of n. Now what you can see is that we have a linear algebra problem that looks like the following. On the left-hand side, I have my temperature data. Those are my measurements. And we know the inputs of time over a 24-hour cycle. Therefore, this gigantic matrix right here, each column just contains each of these entries. It's a vector that runs from 0 time all the way to time tf, which is the last measurement at 24 hours. And so it's going to have 1 along the first column because this has a 1. The cosine of the 0th mode is just 1. The second column is going to have cosine pi t divided by 12. Again, it's going to have a column where the first entry of this row is going to be the 0 time, at time t equals 0. And the last entry along at the very bottom of the row is going to be at time t equal to 24 hours. Okay? And you just keep going. And so this entire matrix, we know all of that. And lastly, here is our unknown vector, all of our weights, the coefficients to this Fourier series. So all I've done is to rewrite this Fourier series as a linear algebra problem based upon our experimental data, our known assumed form of the Fourier series expansion, and then our unknown coefficients. And you can clearly see that you'll recover exactly what we guessed for our model. You just take the linear algebra calculation, A0 times the first entry, A1 times the second entry, A2 times the third entry, and so on. So this first row, if you multiply it out, would hopefully predict at the temperature at time t equals 0. And you move on all the way to the bottom of the column, A0 times this entry, A1 times this bottom row, A2 times this bottom row, all the way will hopefully predict the temperature at time t sub f, which is 24 hours. So this is just a linear regression problem. Just ax equals b. And so if you just invert a, you'll find all of our unknowns, and you know all of your coefficients in front of your Fourier series. So if you go back to the code, that's exactly what I did. So if you look over here, I'm just using a least squares fit to find the coefficients a sub n. And for this particular example, I've just taken 10 modes. So the summation up here is just going to go out to n of 10. So we have 10 coefficients over here, 10 entries of this cosine basis function. And here we're just taking the backslash operator and just solving ax equal b. And out comes my vector a that contains all of my Fourier coefficients. So you could just see here that I'm just adding together all of my modes. So cosine n pi x over 12 times all of my modes out in front will ultimately give me the temperature profile. So in this particular case, we're not using a neural network to connect the data inputs to the output of A sub n. We're just using a linear regression, which is still a data-driven approach. We're using data to fit a Fourier series and obtaining those coefficients. So it's a data-driven model. So you don't oftentimes need a neural network or anything fancy to take a data-driven approach. Now let's suppose you were to keep taking more measurements outside your home over the entire year. So you keep doing your experiments, you make a measurement of your temperature inside your thermocouple, you get that reading, and you collect now not only a day-to-day cycle, but you get seasonal cycles. So let's suppose that now you have data on the temperature as a function of time over the course of an entire year. As you can see, that still fluctuates, and if I were to zoom into a particular region, you can still see that it oscillates up and down on a day-to-day cycle. But then there is a slower, longer frequency or longer wavelength variation over the seasonal trends. It's really hot over some months of the year and really cold during other months of the year. And it roughly happens over this 1-year cycle. Now, if I were to take the black box approach and just feed in, for example, 6 months worth of data, so I put in half the full seasonal year, the red curve is what the black box model shows. So you can see that it captures the mean temperature very accurately inside the training region, but once again, like I showed earlier, it fails to predict the temperature outside the training range. But what's also kind of interesting is if you zoom into the day-to-day oscillations, again, there is a 24-hour cycle and the temperature going up and down over a 24-hour cycle, right, over a much higher frequency. The neural network, the black box model, captures the mean of each of these daily fluctuations. And what's kind of interesting is because we're feeding data over the 6-month cycle, it's minimizing the error, the mean error, across this entire range. And so it's saying, well, I don't really care about the couple of degrees of error that I'm incurring on a day-to-day cycle because I'm capturing the overall trend. And because I've captured the overall trend, I'll just capture my lowest mode and call it the day and not capture all the high frequency oscillations. It's kind of interesting that it converged on that model. In contrast, in the gray box model, our physical intuition would tell us that there is going to be this 24-hour high-frequency oscillation cycle, as well as a longer, lazy, large wavelength variation over the annual year. And therefore, we would expect it to have a much slower oscillation hidden behind the high-frequency oscillation. So we can put that into our model. We can say we're going to have a cosine of n pi t over 12 for the 24-hour cycle, and we can have another summation of sines and cosines that represents a much longer wavelength, very low frequency oscillation over the year cycle. And so this is the result of that model shown in green. This is a highly zoomed in model taken over the 24-hour cycle, but again, we're feeding the same data, and if I zoom out, you can really see that this gray box model is not only capturing the individual day-to-day oscillations, because it found all the right coefficients to capture the 24-hour cycle, because we specifically put in, using our physics intuition or physics-derived model, a rapid high-frequency 24-hour term inside the sine and cosine, in addition to a slower, longer, lazier wavelength oscillation that goes over the annual year, and it caught the right coefficient for that. So it's a Fourier series with two very different frequency scales, and as long as it fits the right coefficients in those two frequency scales, you can capture the entire range of data. Again, we're using a lot of physical insight to construct our model in the right way so that it converges to the right coefficients. So this is just another example of the use of gray box and comparing it over a system where you have a separation of timescales. one, largely kind of rapid oscillation data, as well as long, slow, lazy oscillations. So again, it shows the advantage of the gray box in not only extrapolating beyond the training set. Again, I'm only giving a training set between 0 and 6 months, so half the year, but it's doing a pretty good job capturing the rest of the year because we kind of know that the year follows a rough annual sinusoidal cycle. Okay? There's actually a lot of things that we're learning from just this very simple example. And of course, I just put some notes here. For the black box neural network model, if the x-axis time is sampled too sparsely, of course it's only going to capture the mean. That's not what we're doing. Some of you might say, well, you're only, the black box is only capturing the mean because you're sampling too sparsely. That's not what we're doing. We're actually very, very fine in our sampling of our data. It's really just biasing towards the mean. So this is a kind of training bias towards the mean squared error. So it's favoring the mean and it's not capturing the error of the high frequency noise because the couple of degrees of swing is less costly than capturing the overall seasonal trends in the curve. All right, so of course this is a very simple example. I wanted to move on to a more interesting and complicated example, but I just wanted to kind of seed in the spirit, the philosophy behind different types of models. Because you can see that in all three of the models we have here, we have some input, time or position, and output of temperature. They all have that input of time, output, temperature, input, time, output, temperature. But the architecture of how you set up that box that connects the input to the output is very different. So they're all very different models. And as a scientist and engineer, we have to figure out how do you use the data in the right way? How do you combine the right kind of physics? How do you let the computer figure out the parts that is really hard and annoying for a human to figure out? That's kind of the main bread and butter of data-driven models in science and engineering. Like I said earlier, unless you're an AI researcher specifically developing the actual neural network itself, for majority of us scientists and engineers, we're just going to be using this type of thing as a tool. So it just comes down to how do you use that as a tool in your science and engineering research. All right, let's move on to a slightly more serious example. It's still a toy problem. Let's do a more complicated example next.